All right, welcome back. So this video is going to cover mole conversions. And what I would suggest you have available to you while you're going through these notes and working these example problems is your green mole concept map that you have. Okay, so I don't won't be really showing that on screen, but you want to be using that as you're following along here, especially when you're first learning. Okay, so the way that we do mole conversions and the way that you want to be using your mole concept map is when you read the problem statement, you're trying to figure out what quantity you're given and what quantity you want to convert to. And again, that mole concept map I find is a very useful aid for doing this to get you started. Just keep in mind that the goal is as you get more practice with these, you will have to be referring to the mole concept map less and less because the key thing to understand is you want to get practice and habit of making sure you're using the correct conversion factor to go between which units, and that is what the concept map helps you out with. And the other thing that we want to make sure we're doing is in your work, you're showing your number, your unit, and the substance. That is a very important habit to get into now, and so that you can be successful later, especially next unit when we get to something called stoichiometry. All right, so in this first one, the quantity that we're given the problem is this 1.27 moles. Now, if you're looking at your mole concept map, you notice moles is right in the middle. Right? I'll just kind of draw a crude one over here. Right, there's moles. This is mass up here. This is particles. And this is volume of a gas at STP. So in this case, we're starting with moles, which is right here in the middle. And you want to get grams. Now, hopefully, in order to use this, you have to understand what units represent what. And grams are a unit of mass. So in this first example, we're just converting from moles to mass. And the conversion factor that's listed there on your concept map is the molar mass. Right, so in order to use the molar mass, we need to know the compound here, nitrogen trihydride, that's NH3. But it's dimensional analysis, just like started with the year, and this is one step. We're going from moles to mass, and we have to use the molar mass of this. So to figure out the molar mass of this, we need a periodic table, and we have one nitrogen, which is 14.01 grams, and 3 hydrogens, that's 3 times a 1.01, or 3.03 grams of hydrogen. So we would say the molar mass of NH3 is 17.04 grams per mole. Again, we can write that as 1 mole of NH3 is the same as 17.04 grams of NH3. And this form here is going to be less confusing for you because this will help you understand, okay, I can break this up into 2 parts so I can place it in my work. And again, you need to place it such that the units cancel of what you're trying to get from, and the units that you're trying to get to remain. So hopefully you know or remember from the beginning of the year and dimension analysis is that, okay, if I've got moles here, if I want this to disappear, well, the moles has to be opposite of this, right? You can think of this as being just over 1, if that helps. So I need to put the 1 mole portion down here, and the 17.04 grams of NH3 goes up there. Right, so that I can go back and I say, check my work, that moles cancels out with that moles. I'm left with grams, which is what I'm looking for. Then I just have to put that into my calculator. And the calculator says this value 21.6408. Remember, the molar mass is a conversion factor. It is a defined constant. The 1.27 moles, however, is not. So we have to round our answer to three single figures, which is 1, 2. We've got to round to the spot. Look at it. The number behind it's a 4, so we're just going to truncate. And say 21.6 grams NH3. Next one. How many moles are in 77.5 liters of carbon tetrahydric gas at STP? Well, liters is a unit of volume. And we've told it's gas at STP, so we're starting here in this problem. And we want to go to moles. So we're just going from here to here, one step, and we're using the conversion factor that's listed on your conversion sheet or your concept sheet as the molar volume of a gas at STP. Again, mentioned this in class, STP stands for standard temperature and pressure, and a standard temperature for gases is 273 Kelvin or its equivalent, which is 0 Celsius or 32 Fahrenheit, and 1 atmosphere pressure or its equivalent. So any gas at STP conditions, 1 mole of it occupies 22.4 liters. So start with this. 77.5 liters of CH4. And the molar volume of a gas is the 1 mole of any gas, so in this case CH4 would occupy 22.4 liters. Right? When the conversion factor is written this way, then it makes hopefully more sense to you. What do I put where? Right? This value is listed on your periodic table. It's just written as 22.4 liters per mole. So that per mole just means per 1 mole. So I'll put the 22.4 liters of CH4 down here, 1 mole of CH4 up here. Put that in my calculator and round. I need to divide instead of multiply. Calculator says 3.4592, whatever, yada, yada, yada. And again, I've got three single figures because the 77.5's got 3. And so I'm just going to round that to roughly 3.46 liters. Or no, sorry, 3.46 moles. Go back and check my work, and I just quickly did when I noticed that, wait a minute, that doesn't make sense as being liters. This next one, my moles are in this many formula units. Remember, formula units is a particle. That means on your concept map, you're starting here, and you want to get to moles. So we're going to use Avogadro's number. And Avogadro's number, right, is 1 mole of any substance is equal to 6.02 times 10 to the 23rd particles of that substance. Now, since we're talking about an ionic compound here, the represented particles are formula units. So the 6.02 times 10 to the 23rd formula units goes down here, the 1 mole, so it goes up there. Now, just as a reminder, when you're entering this into your calculator, you want to be using this type of format for scientific notation, or else you're going to run into order of operations issues. Right, don't use times 10, then the caret raised to the 24th or something like that, because you will run into order of operations issues. And then I just need to divide that by Avogadro's number. And to 3 string figures, that's going to be 12.0 moles of sodium chloride. Next one. How many atoms are in this many moles of magnesium? Well, moles is starting in the middle of the concept map, and atoms, right, that's particles, so that's bottom left. I'm going to use Avogadro's number again. Except instead of this way, we're going to use it in the opposite, in the flipped way, because we're starting with moles this time. So 1 mole of magnesium would be the equivalent That's 6.02 times 10 to the 23rd atoms magnesium. That cancels there. Now notice I'm going to just take this and multiply it by that. 6.02 times 10 to the 23rd times 0.26. Or the two single figures, it's going to be 1.6 times 10 to the 23rd atoms of magnesium. Lastly, how many moles in 45.7 grams of magnesium? Well, grams is mass, so we're starting at the top of the concept map. We get to moles in the middle, so that means we have to use the molar mass, which isn't that hard to calculate because we're just talking about an element here of magnesium. Right, 1 mole of magnesium is the same as 24.31 grams of magnesium. That's just what we did on the other page. So you see the grams here. The 24.31 grams goes here. The 1 mole of Mg goes there. So the three single figures, you get roughly 1.88 moles of magnesium. Okay, so those were mole conversions. They're single-step problems. Now we're going to go on to two-step problems. So we read this. How many grams, okay, grams, hopefully you're thinking mass, are in 352 liters of carbon dioxide gas at STP? Okay, when we see the fact that it's a gas at STP, that makes it okay for us to use the molar volume of gas down here. One problem that you may get confused about or use in air, even next semester when you learn other types of mole conversions, is that, right, liquids and gases have volumes. This molar volume of a gas is not going to work for a liquid. So that's more of a next semester issue, however. But gases at STP, okay, we can use that 22.4 liters per mole. But in this case, we're starting here, and we want to get to mass. That's a two-step process. We have to go to moles first. Right? If you are not given moles, you're going to have to find moles, no matter what type of conversion you're doing. So just that, as you get more practice with the concept map, you'll realize, well, wait a minute, well, if I don't have moles, I'm going to have to find moles and then possibly convert that into something else. So start with a 352 liters of CO2. Got two steps here. First one is using the molar volume of gas to convert it from volume of gas to moles. And then the beauty of dimensional analysis, right, is your work will set itself up. You see the liters of CO2 means the liters of CO2 goes down here. And this moles of CO2, well, we don't want moles, we want grams. You know in the next step, this moles of CO2 has to go down here. Remember the second step from your concept map, right? We're going from moles to mass. So we have to use the molar mass. And this is CO2 we're talking about, which consists of 1 carbon, 2 oxygens. So 2 oxygens is 2 times 16, that's 32. That's another 12. The molar mass of CO2 is roughly 44.01 grams. The mole we already know goes down here. That means the 44.01 grams of CO2 has to go up here. And then I can just put that into my calculator. 352 divided by the 22.4 times the 44.01. And to 3 single figures, I get roughly 691 or 692 grams of CO2. Remember, there can be a range of acceptable answers. Some people will do this first step, round to single figures, then do this next step, then round, and so there's going to be a slight variation. Okay, so that's why you always show your work, so that we can see how you did it and so on and so forth. And also make sure you are going through and including the unit and compound, each one. Okay, I know it may. You can do it without, however, you won't be able to check your work. And it is kind of why we learned dimension analysis in the first point of using your units to set up your work. So you will not get credit if you're not showing unit and substance. So it's a good habit to get in sooner rather than later. Next one. We are given grams, right? That's mass. We want atoms, which is particles. So on the concept map, starting here, we want to get to here. Again, this is 2 steps. And you notice, when in doubt, you're going to have to find moles. So start with the grams of carbon. You will need to convert that first to grams. From grams to moles, and then from moles using Avogadro's number to particles, or atoms in this case. So you look on the periodic table, the formula of carbon is C, and the 12.01 grams of carbon goes down there, the 1 mole of carbon goes on top, so the units cancel, and then this 1 mole here tells me, okay, this goes down here. The Avogadro's number, the 10 to the 23rd atoms of carbon goes on top. Look at this, grams cancel, moles cancels, you're left with just atoms. 26 divided by 12 times the 6.02 times 10 to the 23rd, or roughly 1.30 times 10 to the 24th atoms carbon. And our last example is a little bit trickier, because you notice we're looking for sodium ions, sodium sulfate. Now, key to this one is, well, you need to know what the formula of sodium sulfate is, right? It's not NaSO4, it's Na2SO4. So sulfate's -2, sodium's +1, need 2 sodiums. Now, when we're talking about ions, if you have 1 particle, 1 formula unit of sodium sulfate, you have 1 sulfate ion and 2 sodium ions. So in 1 sodium sulfate formula unit, you have 2 of these ions and 1 of these ions. So this is mass. So we're starting here. We want to get to particles, which is down here. But when we get to particles here, that's going to be how many formula units of sodium sulfate we have. We will just have one last step of converting formula units of sodium sulfate to actual how many sodium ions that would contain. So this will have 3 steps. And there can be some variation in how you go about doing this as far as the steps. However, mathematically you should always end up with the same answer. So I start with this, and this problem here is a good example of why you need to write the substance along with the unit with your number. Because if you don't, you're going to get lost, and you're not going to know what you need to do. So the first step is we need to convert mass to moles, and that is molar mass. So as you get more hang of this, well, if I'm doing molar mass, the 1 mole part always goes up, is going to go up here in this case, because you've got grams down here. Then I need to calculate the molar mass of this. So I've got 4 oxygens, so that's 4 times 16, put that in my calculator. Add a sulfur, which is 32.06, and add 2 sodiums, and that's 141.86 grams. Now, if I convert this to particles, to formula units, 1 mole of Na2SO4 contains 6.02 times 10 to the 23rd formula units sodium sulfate. Okay, so to this step, this cancels here, this mole cancels there. I've got formula units of sodium sulfate. And the last thing I need to do is I need to figure out in 1 formula unit of sodium sulfate, how many sodium ions do I have? Right? Again, this unit has to go down here for it to cancel. So 1 formula unit of sodium sulfate contains 2 sodium ions. Right, so that's my third thing that I need to use. And then I'm all done. calculator. Times the 6.02 times 2. Or roughly 5.81 times 10 to the 23rd sodium ions.